Okay, I would like to give some overview of the architecture of Spark, just to see how it is built. So we want to see the Spark software stack, and we want to see how these RDDs are built, and we want to see when the Spark runs, when we run a job on it locally, and our job on a clustered environment. So we will see also an example of a machine learning library used with Spark. So as we mentioned, the Spark is designed to be a cluster computing platform and to be fast and general purpose. So it was designed as an improvement to MapReduce because we want to be fast and general purpose. So the Spark extends the MapReduce model to efficiently support more type of computations, including interactive queries and stream processing. And so we said speed is important. If something takes minutes and it takes hours, it makes a big difference. So it has become right now pretty much an industry standard for data analysis on a cluster environment, and it is replacing MapReduce computing engine. Even the Cloudera is even saying that they might retire the MapReduce in future versions. So the Spark does not use MapReduce as an execution engine. It has its own execution engine, as we mentioned. So it has its own cluster manager, and it can be installed in standalone mode. If we do have Hadoop or Yarn or Mesos or something else cluster manager installed, it can run on top of those. So it can be run via Yarn, and you can use the Hadoop file formats and the HDFS storage. So it is best known for its persistent large data sets in memory. So when we switch between jobs, it is able to hold large amounts of data in memory, which significantly speeds up the processing compared to MapReduce. And it is written in Scala, as we mentioned. Scala is it's based on Java, and it's a language for scalability. So it allows for much more concise syntax than Java. And so it does have support for Java and Python and R and other languages. So this is the Spark software stack. We mentioned the core is where these resilient data storage partitions are created, and it provides the APIs for storing data and code into these RDDs. And it can, however, connect to other file systems. So it can retrieve and store files into the Hadoop distributed file system, into the Google parallel file system, and Cassandra and other file systems. And as we mentioned, the scheduler or the cluster manager for Spark, it has its own standalone scheduler. So if there is no cluster manager installed, it can run in its standalone scheduler mode. If we do have Yarn or Mesos, we can run the Spark via Yarn on a Hadoop cluster, or it can run on top of this Mesos. So the libraries that it provides, as we mentioned, it has support for SQL, structured data, so it can lead to five tables and JSON tables and other tables, and then the Spark stream and run SQL queries on them, the streaming real-time engine. So it supports Kafka, which is another Apache's project for design, especially for getting incoming streams of data. And so it manages the stream, and if there's any issues, it can repair them. So the streaming library can integrate with that. Also Flume 6. The other library is the machine learning library. We have seen for classification and clustering and linear regression and other machine learning tools. And then the GraphX is for processing large graphs. So this is how the software stack looks like. So let's see how we can create these resilient distributed data sets. So RDD stands for Resilient Distributed Data Set. So they are read-only, and they are collections of objects that can have partitions. Now, these partitions can be chosen and defined by the user. So over here, if we want to create a new RDD, we say the number of partitions equal to 10, create a new Spark context, master, test app, and so we can define that the number of partitions is 10. So in this case, we created the RDD by loading a data into it. So when data has no parent RDD, the input file and the number of partitions is set according to the number of cores or nodes on which we will execute them. So this means it's gonna take 10 nodes to process this data. Now we can, that's statically defined, or we can parallelize existing collection of objects by passing a list set. So again, number of partition is 10, and then we are passing a list. So we mentioned that this RDD can be created in two ways, either by loading external data set or by using distributing a collection of objects, such as a list or a set in their driver program. The operations that we can perform on them is either a transformation. In this case, if we have a transformation, we will return a new RDD based on the previous one, and it is transformed in a lazy way. In other words, they only transformed when you use them in action. Some of these transformations are what's called element-wise, so they work on one element at a time. example of a transformation here is a map function. So return a new distributed dataset form by passing each element of the source through some function. That would be a transformation. It's going to take the original RDD and transform it into a new version of it. And so it will return a pointer to the new version. If we run a filter, it's the same thing. It goes through the current RDD and it will look at some elements from it and create a new RDD. Now, if you want to take some action, perform some kind of computation based on the data, such as aggregating elements, then that's an action. So the action operation will produce some output based on the RDD. Let's say it wants to aggregate